Okay, so Michael Nussbaum will be giving first steps in quantum mathematical statistics.
Okay, I will give a Blackboard talk mostly. Only at the end, if there's time, which I doubt, will I come to slides and give more of a research level section, but it's unlikely. I think I will stay with the introduction on the Blackboard. So, quantum statistics first steps. So I will first try to focus on the formalism, so a purely formal approach. What kind of probability setting is this? Different from the classical we know. And then I will talk a little bit about the physical background, just only a little bit. And then go on to the statistics subject, which is the quantum Lyman-Pearson lemma, the analog of the Lyman-Pearson lemma in the quantum setting. So first, to understand what quantum statistics is, let's begin with a very simple setting. So we have a classical probability space, finite. This is finite, so we have we have a random variable. X is a random variable, and the probability that it takes value xj is pj. I write the expectation. P is the probability measure, P1 to P k, P1 to Pk, and so the generalization will be first a generalization of this finite probability setting. So of a finite probability measure. So the expectation is expectation of a random variable x. So the values are x1 to also xk, and the expectation is of course sum over xj pj. Okay, now let's come to the first generalization. So generalize. We try to generalize it, and this is the first generalization. And this quantum probability uses complex numbers, but we will try to capture that first, the essence, not using complex numbers. So using only real numbers. So in this, it's not the actual quantum probability, but it's a kind of caricature of this state of a physical system. The state of a physical system is a non-negative symmetric K times K matrix. So that rho, let's denote this rho ij, and ij goes from 1 to k with trace 1. Trace 1, so trace of rho is sum of the diagonal elements, rho ii equal 1 to k is 1. So, okay. So symmetric means, of course, rho is equal rho transpose, and positive definite. This means greater equal to 0. Or say, no, let's okay, greater or equal. We do not require strict inequality. Positive symmetry for all x. X for all x element rk. So we call this positive as usual. Positive. Now let's recall the spectral decomposition of a symmetric matrix. Spectral decomposition. We have rho is can be decomposed using the eigenvectors and the eigenvalues, j1 to k, and so E1 to Ek is an ONB or orthonormal basis of Rk, and Ej, of course, is the pertains to eigenvalue number j. So another way of writing this one is, of course, in terms of matrices, C lambda C transpose. So lambda is diagonal, the diagonal matrix of the eigenvalues, lambda 1, lambda k, and these are the C are is the matrix, the columns of which are the vectors E of the orthonormal basis. So we can write it like this. So orthogonal matrix. So C transpose C is unity. So okay, that's the state of a physical system, a matrix. It's so now what are measurements? I can immediately mention that we will get a classical probability measure as a diagonal matrix. So if the trace is the sum of the diagonal elements, so if the matrix is diagonal, all the elements must be positive on the diagonal and they sum to 1. If there are, all the rest is 0, if it's diagonal, we get a classical probability distribution. So in this way, classical probability with a finite dimension, finite probability, is a special case. But I will come to that in more detail. Now, what are measurements? So measurements, so they generate random variables. The specific feature of quantum probability is that we create random variables. They are not there already. We have the choice among many random variables with their distributions, and we create them first from the state. And they are created using a measurement by a measurement. Create random variables by a measurement. So a measurement, so we can write it as M is a symmetric matrix. Symmetric K times K matrix. So this time it's not necessarily positive. It can be any symmetric matrix, and we can again write the spectral decomposition xj, mj, m transpose. So let's say j1 to k. Xj can be numerical values. So xj, of course. So x1, xk. Consider only with real values, so the finite subset of the reals.
So those are little x.
These are little x. The values which the measurement can take. So that's analogous to these. They are also lowercase x. So these, by the measurement, we create random variables, and the random variable takes values x1 to xk. So this creates a random variable x sub n. The values are the eigenvalues, x1 to xk, which are here, the eigenvalues of the matrix M, and the probabilities are probability that xm takes value xj, mj transpose rho mj. So this is under the assumption that if if all xj are different. So we of course we can have measurements where we have only two different xj's, maybe 0 or 1. So some of these coincide, and then they are not all different, and otherwise, so we xm takes one value xj is the sum over all mi rho mi over all the I. The xi is all the I where xi is equal to xj. So sum of xi equal to xj. Some of them are the same, so we sum over all those which are the same for one particular case, and sum of these values. So mi transpose rho mi. But we can take this case here as the model case. So to understand what's going on, look at this case where it's a one-to-one map. So all the xj are different, there are k of them, and there are also, this is on Rk, so the state has k different eigenvalues. So, okay, why is this a probability? What is generated here? Is this actually a probability distribution in this mechanism? So we see that what enter here into the random variable, the random variable takes the values xj, which are the eigen values of the matrix, and the mj are they also take part in this process. They define the probabilities.
So for different measurements, you just change the eigenspace. You keep the eigenvalues and they're fixed.
For different measurements, I can change also the eigen values. Then the random variable takes other values. I can have a random variable which takes the same values, so I can keep the same eigen values, and I can change the basis. So in this case, the random variable would take the same set of values, but with other probabilities, right? Because they enter here, so you see that mechanism. We have a choice among many random variables in that case. So is this a probability? First, is it a probability? First, they're all positive. So the individual probabilities, mj, because it's positive semi-definite, mj rho, mj is greater or equal to 0. So that's clear. Do they sum up to 1? Now let's take the sum mj transpose rho and sum them up, j equal 1 to k. We can write this as a trace. This one here is also the trace of the matrix rho mj transpose. And that's because the trace is cyclic. So if you have trace ABC, then that's also, you can put the A at the end, so be trace BCA. And so that's cyclic, that means the A goes here, it's still the same trace. And so here I wrote for 2 because I wrote it for 3, but for 2 of course. So here we apply that. These are vectors, and if we put the mj prime here at the end, we get a matrix. So this is a 1 by 1 matrix. This is now k by k. This is mj prime is already a matrix. Now, so this is trace rho mj transpose, and j1 to k. So the trace is additive. That means we can put the so yes, trace is a linear operation on matrices. So we can put the sum in here. This is MJ transpose. And so this one here is the unit matrix. It's the spectral decomposition of the unit matrix. Because the unit matrix, you can write it, the spectral decomposition of the unit matrix, because all eigenvalues are the same. You can use any basis, any orthonormal basis for a spectral decomposition. So and that is, we use this M basis and get the unit matrix. So this is trace rho, and because it's a state, the trace was 1, so it's these probabilities sum to 1. So we have actually have a probability distribution. So now, okay, as a consequence, we can also write expectation in a certain way by using the same trick. The expectation of the random variable we have created by the measurement m, xm. So let's formally start with the definition of an expectation. So that the random variable takes the values xj, which are here the eigenvalues of this measurement matrix, with the corresponding probabilities mj transpose rho mj. And we apply the same idea. That is, the xj are just real numbers, and we put them also in here, and we get by the same steps, instead of here we have the unit matrix, we get the same sum, but with numbers xj, mj transpose, j1 to k. So this is, and now this is m. This is the spectral decomposition of the matrix M. So we get trace rho M. So this is the trace rule. It's called the trace rule. So sometimes quantum probability is introduced like that, by introducing the trace rule first, and then because you have all expectations, you have all random variables. But the other way around is, I believe, more instructive. We generate the probability distribution and the random variable by a measurement. So now classical probability has a special case. Classical probability as special case. Suppose, so I already mentioned that, we can consider states which are diagonal matrices. Row 1, row 1, 1, row k, k, diagonal. So because the trace, they must be positive or non-negative, because that's a non-negative definite matrix. The trace row is 1. Trace row is 1, which is means the sum is 1, so they are a probability. We have also, but that's true, we always have a probability, finite probability measure on the diagonal. And now we can, suppose we fix a certain measurement. So measurement. So we use, or we fix a class of measurements, not all measurements, but a class of measurements. That means the eigenvectors, the eigenvalues we leave variable, but fix the eigenvectors, use the particular orthonormal basis, which is, let's call this eta, which is the standard, eta 1, the eta k, or canonical basis. Canonical basis in Rk. That means, so the eta k 0, 0 case we get M. So M is a diagonal matrix. So M xj, in this case, eta j transpose is a diagonal matrix as well. So it has now the values in the diagonal. The values it can take it has in the diagonal, and we are simply we have created the set of all possible random variables, which are all ordinary classical random variables, which are on this finite probability space given by these diagonal elements. So xm. So the probability that the random variable xm, which takes any x here, any possible values x, but the fixed basis eta j, the probability for this, that it takes this particular value, is, because the eta j's are now fixed, rho eta j transpose. So these are the canonical basis, which gives us the diagonal element, rho ii, and or rho jj, and we call this pj. So this is the class of all classical random variables. On this finite probability space is a subset of all the random variables which are possible in this quantum setting, because we have fixed the orthonormal basis, the canonical one, eta 1, eta k. We still have create all possible random variables by letting the xj be different. So all the values they can take are still possible, but the m is now fixed, it's the canonical basis, and the probabilities are given.
So Michael, can I think of this as another way of encoding the k-1 simplex? All the points in the k-1 simplex for the orthonormal basis actually.
Yes. Yes, of course.
Okay.
Yeah.
Okay.
So there are things like representing all the states as a set of matrices similar to a simplex and geometry like that. That's also possible. Okay, classical probability is a special case. So in this finite, everything is in the most simple finite setting here. So let's take an example, qubits. Qubits are 2x2 states, so 2x2 matrices. So which would give us Bernoulli distributions. If we consider the classical case, we have Bernoulli distributions, and all the random variables we can create, starting from a row. A row is a 2x2 symmetric matrix, 2x2 symmetric. Trace row is 1, and row is negative definite. The random variables take at most 2 values, so they are of Bernoulli type, but they can all be different, take all different probabilities. So consider a qubit row, a spectral, which is a diagonal, 1 minus epsilon and epsilon, 0, 0. So here we have, on the diagonal, we have Bernoulli distribution. So there are cases that first the one, which is the one I just described, we now try to get all classical random variables on that. So we use canonical eta 1, the canonical basis 1, 0, eta 2, 0, 1, and so we get, so we obtain probability P1 1 minus epsilon, P2 1 epsilon. So that probability space. B, the more general quantum case, M1 and M2. And this is so a general orthonormal basis. And then we can create different random variables. So for instance, we could, M1 is, so the orthogonal cosine phi, sine phi, and M2 minus sine phi, cosine phi. So this is the general form of any basis, of an orthonormal basis. Let's give a picture. So this is the canonical, and any other basis is that, and we can let this rotate. So we can use any other basis and get the whole set of random variables. Now from this let me go to the now a bit of physical background, how this has arisen historically and has been proved, and subsequently this whole framework has been developed. And how is quantum probability observed in nature? So I actually do a bit of physical background here, but in a very condensed form. So first, pure states. What are pure states? Pure states. They are the most important subclass of states where the rank is 1. If the rank rho is 1, then it has representation as follows. Because the spectral decomposition, so there's only one vector. Let's write this E and E transpose. So this is the spectral decomposition. One eigenvector, one eigenvalue is 1. The others are all 0. Okay, that's non-negative definite. It has trace 1. E is a unit vector, so this is 1. Then it has trace 1. They are, yes, the most important subclass of states. And so what can happen with these pure states? The pure states, here it is very visible what can happen. In one measurement, we get deterministic results, which are not random at all, and in another measurement, we get random results. So that is the mechanism where randomness arises naturally in practice, quantum randomness, and I will come to the experiment where it has been shown, the most famous one, the Galact experiment of 1922. So consider measurements. Consider two different measurements. First, M uses a basis, uses the basis E, uses this eigenvector as first element of a basis, and so consider 2, consider dimension 2, so we have qubits. We explain it in the case of qubits. So we use the basis E is E1 and another one E2. So we uses E1, E2, and the first element of which is the spectra, which represents the state. In that case, what are our probabilities? So P1 is E1, rho 1, E1 transpose. So this is E1 is E, so it's E transpose, rho is E, E transpose. E1 is again E, so this is 1, this is 1, we get 1. One of the probabilities is 1, the other is 0. And that means it's deterministic. So the random variable, which is created from this measurement, and let's call that, it takes the values 1 and 2. So E1, let's write the measurement. The possible values of the random variable are 1 and 2, and this is associated to the basis, E2, E2 transpose. It means if xm is the random variable, the possible values is 1 or 2, and the probability xm is 1, which is associated to this E1 basis, because the probability is 1, as we have seen here, the associated probability is 1. So this one would be E1 rho E1 transpose, and we just computed this to be 1.
Michael, is there a plus sign between those two objects?
Right. Sorry, I wrote nothing, so it's plus. That means it's a spectral, it's a measurement. We give it in the form of a spectral decomposition with eigenvalues 1 and 2. So the random variable which we create by this takes the values 1 or 2 and associated to the basis E1, E2, and one of these elements is the actual eigenvector, the only for non-zero eigenvalue of the stable. So this is deterministic. So the random variable is degenerate and deterministic. At the same time, if we use another measurement, we get a really random result, and we can actually get the 1/2 uniform resolution. And this is easy, because now let's take F1, F2. This is another orthonormal basis, which is the following. We can write a picture, because we are still in the real case. We don't use complex numbers, but real. So it's kind of a caricature of, or a cartoon of quantum probability, but all the features are there. So let's use this basis, which is, we can directly draw. Okay. So that means F. So here is E2, here is E1, here is F1, here is F2. So in this case, we have Fi, the scalar product, Fi, Ej, any element of one basis, scalar product with any element of the other basis. So this is 1 over square root of 2. And so the absolute value is always 1 over square root of 2 of the scalar product. Therefore, if we square it, Fi, Fj square is 1/2. Okay, Ei Fj. And that means now we measure rho in another m. Let's call this mf, m sub f. And so I might call this m sub e here. The first one, xme. Mf is this same possible values, 1 or 2, f1, f transpose plus 2, f2, f transpose, but using the basis f. Now, what values do we get here? So we create a random variable x. This was xme, let's call this xmf. Which possible values are 1 and 2. So probability that xmf takes value 1 is, by the recipe, state rho, and one associated eigenvector is f1. So f1 transpose f1. So the rho had representation E. E is a pure state. So this was E transpose. And now we use E1, E transpose. It's the same. And F1. Yeah, F1. Okay. So this is the absolute value 1 over square root of 2, as we have seen, and we see in this picture. So this 1 over square root of 2, absolute value, and so on, possibly with a minus sign, but together we get it's a square of that, we get 1/2. And so the other one is also 1/2, and we have a purely random distribution, probabilities 1/2, 1/2, and measurement on the same state. So in the same state, it's still in the same state row, the system or the atom, and depending on how we measure, we get a deterministic result or we get a purely random result, and we get anything in between if we're depending on the measurement. So now let's describe the first experiment where this was shown to take place, and where they, of course, then they built this model. So this is the Stern-Galact experiment, 1922. So first we need a principle which was also formulated later, or maybe around the same time, which goes now into the mathematical description, but we will now state it, and then we can understand the Stern-Galact experiment. This is called the principle of collapse. Then it's known under a collapse of the wave function. So we need not worry that the wave function is another name for a pure state. The collapse after. So what does it mean? If a state rho is measured, what happens afterwards? Measured with a random variable xj. This is the measurement, or observable, how it is also as it is called also. Xj, the values that we take in the eigenvectors, if it is measured, and so created the random variable x sub m, which with a recipe we know with the probabilities. So probability x m equal xj is associated eigenvector. So that's the recipe for the creation of the random variable. Now the random variable can actually be observed in an experiment, and it has an outcome. Suppose a random variable has the outcome is xj. Any of these is an outcome. So suppose we have an outcome, and what happens to the original system which we observed? Then the system collapses, or the state collapses. The state collapses to a pure state, mj transpose. So the system has decided it wants to take value xj, and after that decision it collapses to the corresponding pure state, which corresponds to the eigenvector, the value for which we observe. So that has been formulated later, but it explains the mechanism. So now, a new state. We have a new state after the observation. The new state is rho tilde, which is the pure state mj transpose. And okay, now let's describe that experiment. So it's on qubits, and we observe a particle, and so it's a qubit, and they observe certain particles, photons, or whatever they are. I will not talk much about the actual physical experiment, but give the essence of that. So there is a qubit, so a 2x2 state, and it's in initial state rho, whatever it is. So 2x2 matrix. 2x2 matrix with the usual properties. So now we measure this we measure this in E1 and E2. In this particular basis, so it's the measurement we have here, 1 E1, E1 transpose, and 2 E2, E2 transpose. Whatever the initial state rho were, we can measure in that particular basis with possible values 1 or 2 and observe. And we do that on many particles, and we select only particles for which the outcome is 1. So xe1 is observed, the observed random variable. Suppose the outcome xe1 is 1. Select only those particles. Repeat many. There was this double slit. They sent it through such a device of photons. They came either up or down through slits, and they selected only those who came through the upper slit. They have names 1 and 2. So observe only take only atoms or photons which give a particular outcome. The others are discarded. So select only the outcome, only this outcome. So the state is now the corresponding, because we have measured in that system, state is now E1, E transpose is now that pure state. All the photons we have selected, they are in the pure state. In this pure state now we can exactly do this trick here. We measure now in another one, and now we measure in the other basis. So you would think, so initially before quantum mechanics was understood, they thought, okay, it's in the state, it has to, well, we get deterministic measurements no matter how we measure it. We must get, so if we measure again here in the same basis, if we measure again in the same basis in ME, we get the corresponding random variable, let's say xe2 would be deterministic. So this is always probability 1. We always go through the upper slit. So here it was the 2 slits here. After it went through the upper slit, if we do the experiment again, it always will go through the upper slit. This is measured because we measure in the same basis. Now we take those who went through the upper slit. Now measure in F1, F2 in the other basis. Create random variable. Create random variable x f. I index it with f. It's the other basis, and it's the second random variable, the second measurement we perform. And now we have exactly what is here, because it's in a pure state E, and it's initially in a pure state E, or E1, 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 E1 transpose. We measure in the F basis, which is at 45 degrees, and we get 1/2, pure randomness. So create this random variable, and what we find, probability 1, the random variable 1 will be 1/2, probability F for this random variable takes value 2, will also be 1/2. So in the physical experiment, they measured at 45 degrees. It translated into measuring photons with this double slit. There is some magnetic device before that, but then the photon which came through here, through the upper one, has to decide whether it wants to go left or right. And what is found, half of them decided left, and half of them decided right.
So these slits are sequential in space?
Yes, one after another. It goes on. It can be repeated indefinitely, a sequence. So this is the second step here. So it's 1/2, probability 1/2. So half of the photons went through right, half of the photons went through left. So even though we get a deterministic result, when we measure that again, those will always go again through the upper one, but after that, and then if we measure in another way at 45 degrees, they will go either left or right with equal probabilities. Now it can be repeated. So we select only those who go to the left. So select outcome, we take only those photons who went through here. Outcome xf2 equal to 1. They are in state, in the pure state f1 transpose, and we can repeat our experiment again. So send them again through this device, measure up or down, that measure in the other bases, and we again find pure randomness.
So Michael, this means you can have circular. You can have rings. You still have a linear structure, right?
It has an indefinite structure. So that's for rho. So after this, so up or down. Okay, up or down, and then we up or down. We measure that one. We take only those who are up, and then we take left or right. We measure left or right, left or right. We take only those left, those who go left.
Oh, okay.
Then we measure those who went up to here. We measure them in up or down. So they will be split again randomly, one half. So up. Okay, we take those who are here and measure them again left or right. It can go on like an indefinite shape. And again, we always observe pure randomness. Randomness arises again, quantum randomness, so, out of nothing, so to speak. Okay, so far about this experiment. And so now let's come to a statistical problem, hypothesis testing. And we will look at the quantum Lyman-Pearson lemma then. So suppose, so now it comes also to statistics proper, hypothesis testing. Hypothesis testing is between two states. The natural setting is we have decide between two, so it's maybe the simplest quantum decision problem, two states. We don't know which is a true one, decide between them. Which is the true one? Two hypotheses. So null hypothesis, it's not, null hypothesis. State is low, alternative hypothesis. State is sigma. And we have to first create a random variable where this is, which we can use for this. So how is this done? So we have we use xm. We have to use one measurement, and we have to find a random variable and a measurement. So xm created random variable, create a random variable, and so the measurement is some xj and j transpose. J is 1, 2, 3. We have to find the best measurement, and then which creates a random variable. And after we have a random variable, which should only take it's actually a test. The random variable should be a test, only two possible values, which 0 or 1, and which gives us the decision. So after measurement, we have a classical problem. After measurement, we have to decide between two probability distributions. Classical problem, that is the probability xm is xj, given rho is the true state, when is m transpose rho mj, which we call pj, and the probability xm is xj, given sigma is the true state, is mj transpose sigma mj, and we call this qj. So once we have a measurement, we have reduced the problem to testing between two probability distributions which can be solved in the classical way by the classical Neumann-Pearson method. So the additional difficulty is finding a measurement first. Before coming to that, I should probably go to the complex case, because this is the actual quantum setting. So now complex numbers. We're using these, which is just a generalization. So rho is self-adjoint. Self-adjoint, so that means rho is equal to star complex conjugate transpose. It's still non-negative definite. Non-negative definite. X complex, the vector is complex valued rho. X must be greater or equal to 0 for all x element complex a-dimensional vectors, and the trace must be trace rho must be 1. So this means the diagonal elements are real. So this is just the generalization, which is actually used in quantum probability. Okay, let's now come to the quantum Neumann-Pearson lemma. Neumann-Pearson lemma. We have two error probabilities. So xm uses is the random variable. It's the random variable which is created, and by m, and m is again is a self-adjoint matrix, not necessarily positive. Mj, so here we write it like this, complex conjugate transpose. And we have two error probabilities. Error probability 1 of m. Okay. Phi of xn, let's just call this phi, is a Bernoulli random variable. So this takes only values 0 and 1. That means that's a classical test. We have created a random variable, and on top of this, so which is xm, and takes values x1 to xk, and so now we are in a classical problem, and we define a function which takes a test, so which takes only values 0 and 1, which is a test of that. So on top of the classical random variable, we put a test, and the test makes the decision. So what are the error probabilities? The probability phi is 1 when rho is the actual, the null hypothesis is true. So error of first kind is trace rho m, and error probability 2 of m, the probability that phi takes 0 when sigma is actually true, it's trace sigma I minus n. So in this case, we can, yeah, yes, is that true? Why is that true? We can already set xj 0 or 1. All the eigenvalues are either 0 or 1 for this m. That is the random variable which we create takes already only values 0 or 1. So that means we have created a random variable with k different values, but they actually, many of them coincide. They're either 0 or 1. And that means we have created a test with the possible values are only 0 and 1. They already give a decision for us. And now since we call this also phi, the random variable, which takes value 0 and 1, and according to the recipe which we have, it exactly comes out to this formula. In this case, M is a projection. M is a projection matrix. If you so here's the spectral representation of the matrix M, and if the eigenvalues are only 0 or 1, it's a projection. So M is a projection. And then, so let's check this, trace row M. So probability that it is 1, which is probability phi equal to 1, given that row is the true state. So we have to sum up all the probabilities which pertain to the numbers 1. And that means they are yeah, we can write it. This is M itself. This is M itself. So here xj, mj, mj transpose, and we sum over all j such that xj is 1. Because here we sum over all xj, so some of them are 0, and that means we only sum over those which are 1.
I don't think anyone ordered pizza here.
Okay, sorry.
So that means M can be written, if M is a projector, it has only axes which are 0 or 1. We forget about those which are 0, take only those which are 1. So M itself can be written like this. So here it's 1, so mj, mj star, where the eigenvalues are 1. So according to this, according to the recipe we have, the probability that it is 1, we have to sum up over all mj transpose rho, yeah, given the true state is rho, mj. So we sum up over all those j where, of course, where xj is 1, the others. Okay. So now this is by the same trick. It's a trace of rho, and here's the sum mj star over all those j where the xj are 1, and which is m itself. So this is trace rho m. So we check this first statement, and the other then is complementary, is automatic. It's only two possible values. So rho m and I minus m. And so both I minus m is also a projection. It's also a projection matrix. And we have captured the two error probabilities. Of course, the underlying state changes for the second one. It's sigma. So now every test. So this is a quantum test. In fact, we have identified the class of quantum tests. So a quantum test, we can say, a quantum test is a composition of a measurement with a classical test, taking value 0 or 1. We have already carried out this merger here. We already put them together in some M, and a quantum test is a K times K projection matrix. And that is a measurement or an observable which has all the properties. The projection matrix is self-adjoint and is self-adjoint. Yeah, self-adjoint and non-negative definite. No, okay, that's not necessary for a measurement, but yeah, a self-adjoint matrix. So, and we have the two error probabilities, and the quantum Lyman-Pearson lemma tells us what is the best test. And this is that's stated as a theorem, Hollywood-Elstrom. These are the two authors in the 1970s who found this, who found the quantum Lyman-Pearson lemma, the analog, the quantum analog of the Lyman-Pearson lemma. So what is the best projector? Suppose we have a number pi which is between 0 and 1. And I think, yeah, okay. This, suppose we have a Bayesian setting. We have a linear combination of the two error probabilities. Error probability 1, n, plus pi, error probability 2n. So it's a Bayesian setting. We have the two error probabilities here, and suppose we have a prior probability, 1 minus pi, that rho is true, and pi that sigma is true. So we can state the Lyman-Pearson lemma in a Bayesian setting. And so what is a Bayes test? The one which minimizes that. So we claim all tests fulfill all tests M, which are projectors, fulfill error probability for M greater or equal error probability for R, where R is the optimal test. Where R is what test? Support projection, pi sigma minus 1 minus pi rho, and the positive part of it. So I will explain what that means. So here, what we take the state sigma, the matrix sigma, so multiply it by pi, and subtract 1 minus pi times the other state. So a difference of two matrices, a linear combination of two states. Then we take the positive part. So this is self-adjoint, and any self-adjoint, if A is a self-adjoint matrix, we can take the positive part, namely, which is positive part. I think you know this when so A has a decomposition, A, J, MJ, MJ, transpose some of the AJ are positive, some are negative, the spectral decomposition, then we take only those AJ which are non-negative. AJ. So take, or omit those J1 to K, omit those eigenvalues which are negative, and take only the positives, all those which are 0. So that's the positive part. So we have a self-adjoint matrix, and we take the positive part. Now, support position. Support. This is the support projection. Support projection. That means we have, if we have a matrix A here, support A plus, we add up those expressions mj star, where the eigenvalues are positive or non-negative, but we omit the values aj themselves. So here, it's the same for all the sum over where all the eigenvalues are non-negative, but we write only the vectors or the projections. So these are one-dimensional projections, and the sum of them, that's a projection. Because they are orthogonal, mj is an orthogonal basis, and so each mj transpose is a projection onto the linear space generated by mj. It's a one-dimensional projection. Every such matrix is a one-dimensional projection onto the space spent by this mj. That's of course an unit vector. So they are individual one-dimensional projections. They are orthogonal to each other. We sum them up, they give a projection. So it's a projection onto the space spent by the eigenvectors pertaining to positive eigenvalues. And of course, so support, we can say support A plus, and then it's a projection, and we can say the unit map, identity map minus this is also a projection. It's the other projection. There is a complement of this projection. It's the rest together. So okay. So this is a projection. R is this is a projection matrix, and therefore it is a quantum test. And the claim is now it's the optimal quantum test in the Lyman-Pearson lemma. It minimizes this Bayesian error probability. So the proof, I am not sure if I should give it. It takes a few lines. Unfortunately, I didn't have time too much to look into this again. The elementary matrix theory. Let me discuss one special case. So, if you remember the classical Lyman-Pearson lemma can be stated in the Bayesian setting. It's equivalent to the setting for alpha tests, and we can also get out the case pi 1/2. So in this case, we are actually minimizing the sum of the error probabilities. Yes.
Sorry, could you just state the theorem once more? Just the theorem.
Okay. All tests fulfill this. Okay, this is actually here. For the Bayesian error probability with prior probability pi and 1 minus pi.
That's classical.
No, the error probabilities are not quantum setting, but they refer to every projection matrix. Every projection matrix gives a test, generates a classical test.
No, I meant
there are many of these.
I meant pi itself is classical.
Pi itself is classical, right? All tests, that means all projection matrices, have this have their error probability greater or equal than the error probability of R, which is a certain projector, and which is defined here. Support projection for this matrix, a certain linear combination of the two states.
Thanks.
So the most interesting case is 1/2. Most interesting case is 1/2. Then we have a Bayesian, right? So then it's actually R m is 1/2 sum R1 m plus R2 m, and that is so in this case you don't perform alpha tests, but you treat them the same. It's symmetric. It's maybe called symmetric testing or discrimination. Symmetric testing, it's just discrimination. We discriminate between two states. Discrimination between two states with the error probabilities are treated the same way because we just look at their sum, which test minimizes their sum, and we get this as a special case. So the R is here, so we can omit this. Sigma, we can omit the pi there, because then the projection will be the same. Sigma minus rho, positive part, and the projection, support projection of this. This generalizes the classical Neumann-Pearson theory, because you can specialize case, rho, sigma, both diagonal. If they are both diagonal, what happens here? So sigma I you look minus rho I, and there's a diagonal matrix 1 1 1 1. Sigma k minus rho k. So this is the difference of the two. Then you consider those positions where this is non-negative. So then you have, and you take only, you replace them by 1. So what you will then get from here, 1 1 0 0, sometimes 0, and then it's 1 again, and so on. So it's 1 in every position where sigma is greater than 1. And that means you decide on these, at these positions. These must be understood as the elements of the sample space. On the elements of the sample space where this happens, where sigma is greater than rho, you decide for sigma. So that corresponds to m. You say your test is 1. 1 means you decide for the alternative. So in this case, you decide for the alternative, and otherwise you decide for the null hypothesis, which is exactly the Neumann-Pearson test. So it's really a special case. But it's not, it's interesting, usually it's formulated in terms of a ratio, likelihood ratio test. But here you take the difference. You can also do that. It's the same. And then, so the quantum test looks actually at the difference. Okay, I don't know how much time do I still have. I can go now to the asymptotics. What is asymptotics? What is asymptotic statistics in this setting? What does it mean here? N going to infinity, independent IID observation, and so on. Is that, or should I stop here? Or
well, we could do the Swedish algorithm. People can walk out if they're hungry or when you're tired. Or
I am.
It'll be recorded and posted, so.
When do you think you're going to finish?
Should we maybe stop and
okay.
15 more minutes? No, I mean,
What?
should we have upper bound on the time? Because
As you like, yes.
he wants to know. So.
Yeah.
I only want.
You can leave whenever.
Yeah,
Right?
sure.
Then
But
you
it's-
don't upper
it's
bound
fine
doesn't
enough.
constrain
But
our upper
I'm
bound.
curious, we can continue. It's just
Oh.
I have to go in like
Yeah.
probably 15 minutes.
Yeah, just go when you want to. I think
Okay,
we can
sure.
probably
15
wind-
minutes.
Okay, let's do it.
It's all here too. And PDFs. And I'll scan my notes too.
Thank you.
So what is asymptotics here? Asymptotics. NIID observations. So what is considered here is a tensor product of two states. If we observe IID observations, the analog would be the state which we have is a tensor product. So a tensor product or Kronecker product, AB, remember this one, A1, 1B, AKK, A1, A1B, so multiply, build this new matrix out of the two, which has those blocks here and so on. So the tensor product. So we have tensor power means rho n, rho, n short tensor. So the matrix gets ever larger. And this is a Kn times Kn matrix. So now our error, we still want to do testing, and asymptotics of testing. So what is the best test? So now the two states are rho n and sigma to the power tensor power n. And so the whole theory applies, which we have here. We have an optimal test for any two states, and let's assume we have this Bayesian setting, pi is 1/2, and the optimal test between the two states is Rn, support projection of sigma n minus rho n, and take the positive part. Take the difference and then the positive part. Now, okay. Now, what was a recent problem here was the asymptotics of this, the asymptotics of the error probability, and the asymptotics of the error probability. We didn't write what we did not do here. We did not write out the optimal error probability, R for R. But that's possible. Now, okay, maybe here. So the question, a recent research question, what is asymptotic behavior of error probability Rn for the case pi is 1/2. Yeah, for the case pi 1/2. That is the behavior of the optimal error probability between two tests when you have n IID observations. It's the n quantum analog of n IID observations, what we have here. And for the classical case is the Chernoff bound. Classical case was classical case. That means first there's exponential decrease. So that is well known. If you have two hypotheses, and these are fixed, and you have more and more observations, your error probability of deciding between them decreases exponentially. And the exponential rate is known as the Chernoff bound. This is the classical 1953 or so. And the question, what is the quantum Chernoff bound? That was an open question, and this was solved in 2006. And let's give that result. The quantum Chernoff bound. So what we do, we take the error probability for the optimal test, and we take pi1, symmetric Bayesian setting. Now we know that goes to 0 exponentially, and what is common in that with rate n, and so the rough rate, the rate will be always usually for these kind of problems, whatever. I write a question mark for the exponent, for the multiplier. It's usually the rate is e to the minus n something, and to find that something is wrong. There's the Stein lemma and so on in various settings, and the classical Chernoff bound answered the question, what is this factor or this exponent here in the classical case? And now we take the same. So what is common there? One takes first to get hold of this factor. We take a logarithm of the error probability, and then we divide by n. So error probability of the error probability of mn of the best test. So if the error probability mn roughly behaves like that, decreases exponentially, the way to access this exponent there is to take first a logarithm, so you get rid of the exponential, divide by n, so you get rid of this n, and look at this limit. This is the standard approach for large deviations and so on. So one takes logarithm of the error probability, divides it by n, and looks where it is going. And so here in the quantum setting, we do that as well. Logarithm 1 over n, and then we take first the lower bound. There are two parts of this result, the upper and the lower bound. And the lower bound, this is one part. It's infimum 0 s1 of logarithm trace rho 1 minus s and sigma to the power s. So yeah, this is the quantum Chernoff lower bound. So it's the lower bound which provides one part of that result. So one takes the two states, takes them to the power 1 minus s into the power s. So how we do that is clear. We do the operation on the eigenvalues, multiply them, and take their trace. And then take logarithm, and then the infimum over all the 1s. So if you look at the classical Chernoff bound between two probability distributions, we have P, let's call them P and Q. It's of the analogous type. So what you do here, Pi to the power 1 minus s, Qi to the power s, I equal, it's a k-dimensional finite probability, same expression, logarithm infimum 0 between s1. The general form of the classical Chernoff bound for the optimal exponent in deciding between two probability distributions was that. So this, we generalized that to the quantum case, rho sigma. The point here was that in general, rho sigma do not commute, not commuting. If they would commute, that would be a trivial classical case of the Chernoff bound. what you always have, so obviously you need to generalize this expression to matrices, and there are always several ways to do that, because exponentials, logarithm, all that stuff, they do not well, there are the usual problems with non-commutativity. So there were several candidates for quantum analogs of that, and we found this was the correct quantum analog by giving the lower bound. That was a statistical proof in the sense of typical statistical lower bounds. Methods cannot be better. And then the other part, this was shown by some colleagues, mathematical physicists in the same year, and they showed so they showed the other inequality. So here, Ling sup of that is upper bounded by that expression another way, and that was what they did. This was matrix, or matrix analysis, you could say. Advanced matrix analysis, an interesting inequality.
And what year was that?
This was shown in 2006. Both results in the same year. And so what we heard from quantum statisticians that was open for a long time, the quantum Chernoff problem, for 20 years or so.